Okay, you've finished chapter one. Hopefully, you're caught up on your chapter one homework problems. Uh, Chapter two um, gets a little harder. Now, I wouldn't say dramatically harder, but chapter two gets a little harder. And the other kind of neat thing is then we're going to start delving into more very important fundamentals about thermodynamics and helping you become a practicing engineer. So, chapter two is all about, it says, energy and the first law of thermodynamics. So, let's look at a roadmap of what we're going to cover in chapter two. So, this video is going to be, so I've busted up this chapter into one, two, three, four, five, six important topics and might spend some significant amount of time on each of these topics. But this video is going to start with what we call the energy of a system. And remember, in chapter one, we dabbled in that, right? So I brought up, we're going to talk about there's different forms of energy. I said one of the forms of energy is internal energy, and I'm not going to say much about that. Well, we're going to say a little bit more about it now. Then we're going to go into what's work, define work and power. You may have had some exposure to work in high school physics, heat transfer and heat transfer rate. I'm going to suggest that you have a good kind of physical experience feel for a lot of the basics of what heat transfer is all about. We're going to talk about ways you can transfer work into heat and heat into work. Then, one of the most important fundamentals of this whole course is called the first law of thermodynamics. That's where we balance different forms of energy. Very powerful problem solving tool. It's fundamental. And then finally, the last section in this is going to be, I'd like to talk about the first law of thermodynamics for a cycle. And so remember, back in chapter one, one of the sections had to do with a special type of process called a cycle. So let's go ahead and talk. Those are the sections. So let's talk about the energy of a system first. And so let's see what goes into the energy of a system. Remember, energy is a property. It's a property of a system. And this capital E, that would be the extensive property energy. So that quick review, the types of energy we've already discussed. Kinetic energy, but I'm going to go ahead and say what it is. You can derive in probably, I'd say in your mechanics class, right? 1/2 mass times velocity squared. That would be a measure of the kinetic energy of a closed system. The potential energy of a system. Well, that remember, potential energy was a measure of energy above some datum, like the ground. That would be where Z equals 0, but your mass is elevated above that level. And so the definition of potential energy is going to be mgh, where m times g, of course, is the weight of the system times the height, h, above the datum. I think in one of my previous videos, I called that Z. Okay, but you get the idea. I put the important stamp on internal energy, capital U, and that's one of the big purposes of this video. And then I've lumped in other forms of energy I call OE, like magnetic, surface tension, and electrical energies. And I'll just close to you real quickly that, look, we cover so much ground in this ME 2134 that we really don't touch problems associated with other energy. And the textbook doesn't even bring it up in its various, some of the fundamental statements, doesn't even bring up the topics of other energy. Okay, so let's imagine a piston and cylinder, or in other words, a closed system going from state one to state two. Remember, that was an important word, a state, characterized by different properties, state one to state two. And it's going to go and undergo a process to get from state one to state two. And so I would expect, since we're changing states, I would expect the energy of the system perhaps to change. So this is sort of a formal definition of the change in energy, delta E, of the system for a closed system undergoing a process. It's going to be equal to, so the change in energy of the system, like you visualize here, is delta U, change in internal energy, change in kinetic energy, change in potential energy. I believe that's where the textbook stops, but I'm going to add in change in other energy because my first thermodynamics professor, he was a chemist by trade, PhD chemist by trade, and he just loved delving in some other forms of energy in addition to these first three traditional mechanical engineering forms. Okay, so let's do a little example problem to get started. Let's determine the kinetic energy of a bowling ball. Let's quantify that. The mass of a bowling ball, I've shown it here in the sketch, is 7 kilograms. Notice how I've drawn my sketch. I put a little dash line to show that the bowling ball is the closed system. A bowler rolls the ball down a level alley at a speed of 8 meters per second. So you know the velocity. Determine the kinetic energy of the bowling ball. Now, in my problem statement, I don't say determine the kinetic energy in joules or in kilojoules. A good self-respecting engineer has got to know that. So expect that type of question on a quiz or a test, not determine the kinetic energy in kilojoules. That's a little bit of a lightweight. So an engineer should know the units that you're going to result in. Either joules or kilojoules will work. All right, so let's go through the math and the units. Kinetic energy is 1/2 mv squared. That's the fundamental. 1/2 m, 7 kilograms. V squared, 8 meters per second, all that squared. And so let's do the math and carry our units through. I'm going to jam those numbers into my calculator and get 224. Units, kilograms, meters squared, because I'm squaring that, divided by second squared. Uh-oh. That doesn't look like joules or kilojoules, does it? Okay, we're going to have to check that. All right. So we've got to get a little clever. And as we study these units, do you see, if I can split out this meter squared into a meter in the numerator and a meter in the numerator, I can quickly see, okay, that's kilograms meters per second squared times meters. Oh, that term, kilogram meters per second squared, is a Newton. Okay, I've got 224 Newton meters. Wow, okay, I've written that down. And then I remember, oh yeah, a Newton meter is a joule. So in my solution, I'm going to write down the kinetic energy is 224 joules or equals, identically, I'm going to slip the decimal point 3 places to get 0.224 kilojoules. And there it is. I've done the problem. Makes sense? I hope that example problem, it might be something you can go back to if you need to, if you get embroiled in a homework problem and you need to go back and look at a simpler example. Let's calculate the potential energy of a bowling ball. So here in my sketch, it says the mass of a bowling ball is 7 kilograms, just like before, same bowling ball. Determine the bowling ball's potential energy when it is located 3 meters above the ground. And that's my datum. Okay, so I started with a sketch. Here's my closed system. I've labeled it as such, like 7 kilograms. In my sketch, I'm showing I'm 3 meters above my datum line, and I'm going to write out that G is 9.8 meters per second squared. Even though it's not given in the problem statement, I know that bowling balls exist on the Earth. And I guess I'm not familiar with any other bowling balls that exist that are not on the Earth. So I think we're safe on that. Okay, potential energy, our fundamental is mgh. Okay, M, 7 kilograms. G, 9.8 meters per second squared. H, 3 meters. All right, let's do the math and string our units along. 205.8 kilograms meters per second squared times meters. Okay, wow, okay. And so let's see. Wow, this is staring at me. There we go. This first term, kilogram meter per second squared, is a Newton, great, times a meter, 205.8 Newton meters. Same idea. I've got, for this case, for the potential energy of my bowling ball is 205.8 joules or 0.2058 kilojoules. Either of those are going to work if you're in my class. It demonstrates that you know what you're driving for. 205.8, that might get you half credit in my class because you've got to include your units. I've created a separate video, so if you go to my, I got to move around. Yeah. If you go to my thermodynamics fundamentals playlist, I've created a little over a year ago a live demo of a pendulum. I set up a pendulum in my basement and I've got it in motion here, created a video of that to give a demonstration of potential energy and kinetic energy. And so in the sketch, now in the PowerPoint, if you just run the PowerPoint, this very clever GIF sketch, I've got the pendulum's going back and forth and back and forth. And right here, it's reached its top level. And so when it reaches its top swing point, do you see that that's where the potential energy is the maximum because the ball doesn't get any higher. The pendulum ball is at its maximum height above its lowest height that we would set at the datum. And also as it switches, you see, as it switches direction, ultimately the velocity has got to be zero there. And so at this maximum point, it's a maximum potential energy and minimum kinetic energy. And so I'd suggest it just maybe out of interest, just to get a better feel for the interplay between potential energy and kinetic energy for a pendulum. Have a look at that 19-minute video. What I want to do now is visualize capital U, internal energy. And I've posted all of this text out of section 2.3. A lot of words, a lot of text. So let me try to summarize that and get ready. If you don't have time to dissect every word and pause on every single word and reflect on it as before you do your homework, let me try to summarize. What goes into quantifying U, internal energy? Well, that would be molecular movement. And the text author does a great job of three different categories of molecular movement of the molecules contained within a closed system. So you fully realize that, let's say, a piston and cylinder containing air, it's got a lot of air molecules in there. A canister of propane, it's got a lot of molecules of propane in there. A bowling ball, it's a solid closed system. It's got a lot of molecules of bowling ball material, whatever that is. And so the molecular movement, depending on the properties associated with that system, the molecular movement could be categorized as translational movement, rotational movement, and vibrational movement. That's really cool. That, as a mechanical engineer, that's about all I need to think about. I'm not a physicist, so I tend to not think real deeply about things. I'm a problem solver, and I am interested in getting problems solved. So one thing, yeah, so that's what enables us to quantify the internal energy U of the system, because a lot of other folks, a lot of other engineers/physicists have done great jobs, and it's quantified in the book. The textbook shows us how to do that, shows us how to quantify a value for the internal energy U of the system, let's say in kilojoules or kilojoules per kilogram, based on the molecular movement at a certain point in time, depending on the state of the substance. And in my green box, it says, in this course, we do not delve in the details of the molecules within the system. So do recognize we're treating these thermodynamic systems, the stuff that's contained within a piston and cylinder, like air or nitrogen or hydrogen. It is a collection of molecules, but we're going to treat it sort of as one system of a substance that we'd call air or nitrogen or hydrogen, et cetera, et cetera. So don't worry, we're not going to get into the physics details of the molecules contained within a large system of thousands or millions of molecules. Okay, let's use a little Common Sense 101 to just qualitatively think about something. I've got a bucket of tap water, and let's say the mass in this bucket is 1 kilogram. 1 kilogram of water. Over here, I've got a Pyrex bowl, and it's filled with 1 kilogram of water. And it's been heating on the stove for a while, and you can see with your eyes that it's boiling. It's at the boiling point. About what would that be? About 100 degrees C. How about tap water? What kind of temperature would you expect tap water to be? Just in general, what do you think? I might guess 20 degrees C. Okay, so we've got 20 degrees C tap water, 100 degrees C boiling water. Which would you expect to have the greater internal energy? What does your common sense tell you based on that molecular idea? Which closed system do you think would have a higher internal energy? I sure do hope that you said the boiling water. The boiling water has got a higher internal energy. And when we get into chapter 3, we're going to be able to quantify that, and your common sense will be verified. Definitely, there's no doubt about this example. The higher internal energy is this boiling water compared to tap water. So you've got a feel for internal energy. Okay, here's another example using Common Sense 101. I've got a toaster oven in my kitchen. Here's my toaster oven sitting on the counter at room temperature, and there's air. My closed system is the air contained within that toaster oven. Room temperature, 25 C. Okay. Here's my toaster oven with that same air contained in it, and the purpose, and we're heating up that air with the heating rods. We're cooking a pizza, and boy, I don't have a number for you there, but let's guess of what temperature the air might be in the toaster oven here. Well, we know it's going to be over 212. We know it's over the boiling water temperature. It's darn hot. I know that I cook pizza at about 400 degrees F, and right off the top of my head, I can't translate degrees F into degrees C. Well, let's see, 5/9. Let's see, gosh, let's say around 200 degrees C. So that's sort of my very poor arithmetic in my head, but I'll bet you that the air inside this toaster oven is about 200 degrees C. Which do you expect would have a greater internal energy in kilojoules? Well, you know what it is. I'd expect the toaster oven air, the air inside the toaster oven while cooking pizza is going to have a higher internal energy. The air in the toaster oven, higher internal energy. I hope those two examples without numbers at least kind of gives you some confidence that you have a physical feel for internal energy, capital U. So the extensive property, capital U. Now let's get a little more fancy. Let's have a new definition. Little u, that's called specific internal energy. Little u is defined as capital U over M. So here's our piston and cylinder, our gas contained in it, or our substance contained in it, it's got a mass M. So little u, the intensive property, is going to be U over M. All right. You got to commit that to memory. Little u is called specific internal energy, and its units will be joules per kilogram or kilojoules per kilogram. Either of those work. Little u is capital U divided by M. All right, so we're moving along pretty quickly. We've just defined specific internal energy. And now we've reached the end of this module. I declare you a somewhat expert in understanding at least the basics about the property energy. You're able to quantify kinetic energy now. You can get a number with units. Potential energy, you can get a number with units. Internal energy, at least you have a common sense 101 physical feel for when the internal energy of a system might be higher than another situation. Okay. And then we know what the units of internal energy are. Capital U, joules or kilojoules. It's the extensive property. Little u, specific internal energy, joules per kilogram or kilojoules per kilogram. That's the intensive property version of internal energy. So that went pretty fast, didn't it? In the next video is going to take longer because mechanical engineers deal so much in the energy systems area of dealing with work and power. Work and power. And so I do hope from your high school physics, you off the top of your head, let's see how might work be defined in high school physics. Moving a force through a distance. So I hope comes to your work, moving a force through a distance. We'll get through details of that, but work is moving a force through a distance. That's going to be work. Okay, we are going to work through Chapter 2. When you get to the end of Chapter 2, you're going to be a more capable engineer than you were before you started Chapter 2. So that's good news. You're going to get some more homework experience, and I'd say the problems will get a little harder. Okay, good luck with everything, and hope to see you again in the next video.